let's start with our session today. Last session we reviewed the more concepts in C++ in general and specifically classes in C++. But Abdul Hafiz Hojan told me to focus more on C and structs and such things. So I'll try to focus on C and in the same time I will give the code in the C++ style. I mean, it's up to you. I think officially the course code now is in C, but it's up to you to use C. We also built the linked list in C++. We are going to review again the code because it was like fast explanation for the code. And if you want to have the complete code that you can compile, it's uploaded to the course GitHub repository. You have it full code here. So you can reuse it for assignments and sort of thing, like print list, the delete node, the insert node. This is the same code we discussed last session. Okay, we are going to review the code again and also add new features, add delete nodes, but this time we are going to use struct, and then we're going to review again the class, code using classes. Also, I would like to say a little bit about information about something called destructor. Destructor is the opposite of constructor. So the thing that is done for constructor, if you remember, constructor was the thing at initials when you declare the class or the object. The constructor is being called by your code, like for initializing the variable. So the deconstructor is being called when you finish using the object. You want to make a delete, for example. Like in your code, you used free, right? Yeah, so something similar to free. When you call free this object, it will the destructor method is going to be called. We are going to discuss more about it in separate slides. Also, we are going to see how to reset the linked list. I mean, reset, that means all the resources allocated for the linked list we are going to delete. I mean, if we have 10 nodes, we are going to delete one by one. Okay, it's like this. It's like your code, and also counting how many nodes or the length of the linked list. So let's start by coding. Let's code together the code from zero using struct. So the first thing to do is to have defining the node, which is again node contains of data and a pointer called next, right? So we call it a struct node. Inside it we say int or float. Let us make it float. Data, and then we use struct node pointer next. This line means that this is a pointer for another node, which is a struct. So we say struct node star to define that this is a pointer, and next is the name of the pointer. By the way, when you use struct, you are defining that we have this struct. I mean, this is like when we say class point, and then we put the code here, right? This is only defining the shape of the class. And also here the same. This is only defining the shape of the struct. So currently you don't have any node. It's only you say that if any node is created, it will be like inside data and next. Yeah. So what I usually like to use type def to define new type, because in your code, whenever you want to create a node, you should say struct node and let's say head, for example, and struct node 1 or node 2, for example, struct node 3. So whenever you want to define a node, you should say struct node head. There is no way to say node head. Okay, so what I usually like to reuse features from the language itself. So we use type def. If you remember, we took this keyword type def to define new variables. So we simply say type def struct node, and we can name our own new type. So whenever you want to create a node, instead of saying each time struct node, you simply say node underscore t head, node underscore t node 2, and so on. This is again, this is type def. Whatever you put as type. Yeah. If you want to say here a. Yeah. You can name it as you say your meaning to change the name of the type, right? Yeah. So even if you remember, I will also tell you try to make a note. If you remember, we used unsigned and signed variables, right? If you remember, the variables that don't have or don't support minus negative values. Yeah, it was called unsigned, let's say integer. So instead of having unsigned integer each time you want to declare it, you simply say uint, let's say 16 or here 32 underscore t. So you replace this by simply one word. Yeah. And it's very famous to put underscore t, that this means it's a type. I mean, it's not, this is not obligatory, but whenever you see something, a name, and after it under t, this means you should know that this is a type. So let's go to the int main, and here return 0. And again, as we know that we are going to, as we know that linked list is nodes linked with each other with a link with next. So let's say we want to create this link, this linked list consists of 10 linked with 20, linked with 30. So what we are going to do is here we define node underscore t head, and now we assign the data first, because if you assign next, you don't have anything to link with. I mean, head, yeah, the next node is not created yet. So let's start by data. We make it as 10. Then let's create the second node. Let's make it as node 2 and say node 2 dot data. Yeah, correct. And now we put head dot next equal to what? Yeah, for the next should equal to what? By the way, do you see clearly? Let me make it full screen. Yeah, let me make it. Yeah, so to node 2, yeah. But is it like this, correct?
Why we use node 2 for we assign the node 2?
Because now the head is created and contains 10, right? We created the other node and we call it node 2. This is the node that contains 20, right? So you told me that we should assign something to the head.next, right? As long as it's a linked list, you need to make this link, right? So head.next should be pointing to what? To 20, which is node 2. But is this, is this line correct? There is one mistake here. You should see the types and try to know what is the problem. Data is integer, right? Or float. It contains 20. But next it is what? It's a pointer, right? So when you assign a pointer to a struct, this is not correct because struct is not. You should add the and to get the address of it. Okay. So let's create the last node, node underscore t, node 3, and say again node 3. Sorry? Show library?
Can I wait?
Yeah, sure. Node 3 dot data equal to 30. And then node 2 also need to be linked, right? So we say link node 2 dot next equal to what?
Node 3.
Yeah, but what?
We have to assign
Correct. So, but finally, node 3 dot next. Yeah, that's correct. So this is the complete code. So you can write it. So here I just added a log, create the linked list using printf. It's the same of cout the message here with the int l. Okay. So let me just try to execute this code. Linked list.c, and here linked list.c output here output. We have an error. Okay, here we have here semicolon. Okay, so we executed our code. This is in the wrong direction. So here in struct we forget to add the semicolon after defining struct. Yeah, you already added, yeah. So, okay. Now let's add another function to print the content of the linked list. So let's name it as let's call it LL print. LL stands for linked list, okay? And we are going to pass only the address of the head. So it print, yeah. Okay. So we are going to pass only the address of the header, and it's using the node underscore t type. And here we are going to pass the pointer for the a node, complete node.
Why we didn't use next?
Next here like this, you cannot access the variable. Here you are just clearing. If you want like this, yeah, I understand. You can you mean like just like this, right? Yeah, it's up to you. You can. Yeah, it's not wrong. Yeah, as long as you are going to use. I mean, even in the code here, I will going to use. Let's say if I used node, I will say node next like this. Okay. Yeah. So it's not false or incorrect. Okay. So what we are going to do is to check how for iterate through the linked list and print the content of each node in the console. So let me use a new way of defining the method here using what is called recursive. Okay. I don't know if you took like Fibonacci problem, or you remember something like this? Yeah, it's the first example to take when you use recursive. It's like calling the function inside itself. So we are going to call LL underscore print inside itself. So first of all, we are going to say, let's start from the last part. We are going to say lprint node. Actually, I will change my mind. I will use I will just pass the next. Okay. So we need to do this is recursive. I mean, each time you call lprint, it will call each himself, but for the next node. So this code will iterate for forever. You check the node, check the next, and then call himself again to node. So for example, if you just execute it like this, it will go to 10, then go to 20, then go to 30, then go to the other location. It will be null, for instance. But if you have like not if it was not null, because here let's say here you forgot to put null, it will have like initial value which is assigned by a random value, so it will go to another location, or it will good wrong value. So this way it will iterate forever. We should do something to make him stop. When you see node next equal to what? To null. This means that this is the last node in your linked list. So return. This way you break the iteration or the recursive chain. Return 0 or just return. I think return 0. Like this, it will stop. Else, if it has a value, you are going to print the value. So here, printf. If you remember, printf has like formatted way to print the message. For example, I want to say print for me the value of data, and then print an arrow like this. Yeah. So you put the percentage sign, then D stand for decimal, and then the arrow. So here you have one argument, one decimal argument. It will be node dot data. Sorry, not dot. It should be like this. Okay. And here, when you I want to make the print like this. When you reach to the last part, just print X to know that there is no other other nodes left in your linked list. So printf only X here, and to make sure that it will not be in the same line of another message, you just put /r/n here. Okay. Okay. I think here we need to print the value of this node also before printing just print here the node data. Okay. Here and we are going to pass the address of head like this. Let's check. We have okay, we have float, so we define it as a float. So float, we just remove D and put F. Yeah. Any other errors? Return, yeah, it should have not, we should not say 0 because it's void. Where 49, yeah, here we did not put semicolon. Also where? I think it lists 25. Yeah, here also we need to add semicolon. Yeah, so it's 10, 20, 30, and then there is nothing. Yeah. You can add it to your code. This part. So let us just make a small note. If you want to replace this by the old way of using while, let's say, you simply may do something like this. Let's say node underscore t temp, and this equal to let's say a pointer to node temp and equal to node here like this, and you iterate through the linked list using while temp.next does not equal to null. You just keep iterating, and here you do the print. I will not write the code. You just make print the content, and then just update temp with temp.next. Oh, sorry, arrow.next. Okay. Yeah. So this is the other way of writing the code. Now let's see how to implement the reset function. And let us call it ll underscore reset. And again, we are going to pass here an address for the head node. But here, we are going to change something. I may here try the other way. Actually, here you are, the compiler is creating a location for you, but I would use another way to make it more clear that we are creating a resource for each node, or a location. We assign a location for each node more clearly. I mean here. Internally, the compiler is allocating or defining a location for it, and at compilation time, before run your code or execution, and assign the value of 10 to it. But what if we want to make it at runtime? At runtime, we may use calloc, a function called calloc, which is the other type of free. You also use, you already used free, but free is to free the resource. But how to allocate the resource? You either allocate it using the compiler way of at compilation time. The compiler will allocate an address for you, or it will be like in runtime. So you are going to use something called calloc. Let me just use this slide to make it clear here. Yeah. So here I'm just saying that in C++ we have two operator, two syntax we use to create allocation in the memory, called new and delete. Okay, the new will create for you, let's say this is the memory. When you say, for example, here, let's say we have a node, let's say node, and let's say this node is a class, okay, like the old way. Node, let's say n1 equal to, you say new, and then the type of or the name of the class, and just make the bracelets. Okay, so this means he will go to the memory, allocate an address for you, or range of addresses for you, starting from something and end with something, and make it this for n1. So all the addresses will be for n1. Now when you say delete, you just say delete and the name of your variable n1. It will go to n1 and just free it. And now you can reuse this memory location for any other thing for you. So this is new and this is delete in C++. This is in C++. Now in C, instead of a new, you say cmalloc or malloc, depends about the case. And instead of free delete, you use free. Okay. Now malloc works in a different way. I mean, when we going to use it, we use it in a different way. First of all, we define our variable. Let's say we have a struct now. because in C we don't have classes. So we have struct also node, and we say this is as here also. I'm sorry, should be a pointer, because it will return here. It will return for you a pointer. I mean, he created for you the addresses, but you still don't know where this address is. So it will return the address for you, and this should be anything related to addresses should be pointer. The same thing here for malloc node. Let's say n1 malloc, but here instead of you don't have the new, you should say malloc allocation. Here you just say I want to allocate this number of bytes. So here you should say select how many bytes you need. Okay, so here node has a size. Do you remember how to know the size of a variable? There was a built-in function to know. It was in our second session. Size of.
Yes, I know.
Yeah. So you say size of node. This will return the size of variable or the type node in bytes. Size of will do this. So you now have the complete syntax malloc of this number of bytes. Okay. Free, you should say now you finished this line and you finished using n1. You just say free n1 here. So here you pass the pointer or the address of your resource to delete it in the memory like here. So this is identical to new in C++, and free is identical to delete, but you have different way of using them between C and C++. Okay? So now instead of making the compiler do this for me in background, I will explicitly say allocate for me a node and return the address to me in the code. But before going back to the code, I also need to mention that allocation may have problems called fragmentation. This is not related to algorithms actually, but this is important to know when you deal with malloc free. This code is dynamic allocation, and it's called dynamic because this can be done at the runtime. It's not like the compilation time, because at compilation time everything is none. But at runtime you may ask the user to, it's like the assignment, the first assignment, you ask the user to enter the values of the matrix. And so you first need to say, make the user define the size of the matrix, for example. So you cannot expect the size of this matrix, so you should say use dynamic allocation. Okay. So this is called dynamic allocation, but the problem that in memory, like, let's use the graph in the slides. It's more clear. Let's say that you have 8 words. We call the 32-bit as a word. It's like a unit for memory. You already know this term, word? Word. Byte is 8-bit. 32-bit called word. Okay? So each word equals to 32-bit. So here we have 8 words, or 8 multiplied by 32-bit. Okay? So let's imagine this is our memory here in first line. It's empty now. And then using a new, we allocated 8 bytes. Okay? 8 bytes mean 8 multiplied by 8 means 64-bit. Right? I mean, 8 bytes is 8 by 8 bits. So it's 64-bit, right? So 64-bit is 2 words because each word is 32-bit. So you are allocating here 2 locations. Okay, so now in the green it's allocated for you. And then you allocated 20 bytes and the memory is like this. It's almost full. Now you delete A, so the green part is removed. It's free for you now. Again, you allocated 4 bytes, so only you allocate 1 word because 4 multiplied by 8 is 32, and this is 1 word. So currently, your memory has 2 slots or 2 words empty. Okay. Now you want to allocate 8 bytes or 2 words. Okay. Actually, in your memory, like if we want just by eye, we have a 64-bit. Here you have 32-bit, and here you have 32-bit. But when you want to make it as one variable, you cannot do this. You cannot. I mean, the compiler need to use a sequence of addresses. It cannot be like, okay, take 4 addresses from here, from the start of the memory, and 4 addresses from the last part of the memory. You cannot do this. So this case, we call it fragmentation. It's like it's known for Windows, for example. Sometimes you need to use a tool called defragmentation. The tool of defragmentation simply takes reorder your data. How to solve this problem? You simply make a shift. Like you have here, how many? 8 cells. 1, 2, 3, 4, 5, 6, 7, and 8. And this one is allocated, right? This one is allocated. This one is allocated. This one is allocated. And this one. Only we have 2. This is fragmentation. When you do defragmentation, you simply shift the value to the left or to the right. So now you have 2 slots empty. So you can do the allocation, right? So this way you solve your problem. So the problem in dynamic allocation that you may end up by this case, which is called fragmentation. That's why you should be very careful while using dynamic allocation. I mean, it's not easy to reach this state, especially for a memory like the PC. You are talking about 8 gigabytes or 16 or 32 gigabytes of RAM, because dynamic allocation, it's in the execution memory, which is RAM. So you are talking about 32 giga or 8 giga or 16 gigabytes of memory you can use. So it's not easy to reach to fragmentation. But for small devices, you have memory in kilobytes. So it's easy to reach to this state. What else? Yeah, okay, so let's return to the code. So I will stop using this way. Instead, I will do the malloc and say this is a pointer for head and it's equal to malloc. And do you remember what here we should put? The number of bytes inside malloc. Here we should put the number of bytes we want to allocate. Yeah, so here we should use size of node t. Okay? Now we can access to head you can see here, like here we use dot because it's not a pointer. Here is a pointer, so we use arrow. Okay? So now data equal 10, and then node underscore t, node 2 equal also malloc, size of node underscore t, and we should say head next equal to what? Yeah, and here we don't use the AND operator because it's already a pointer. So we are assigning a pointer to a pointer. I should say node 2 data equal to 20. Let's make it fast. Node 3, and here node 2 next equal to node 3 and 30, and finally node 3 dot next, sorry, not dot, arrow next. Yeah, correct. So let's see if this is going to work first by calling the ll print, just to make sure we did not make any mistake. And here again we are not going to pass the address of head because head is already a pointer. Okay? Use the code I already prepared here. Let's just remove the reset here. As you can see here, the function called print linked list, it has the same way we already used. When you reach the node next to the end, you print and then return. And here we create also using malloc size of node. This is the same way. And then the tail, and we tail next equal to null. And then we print the linked list. Okay, so reset. Now let's move to reset. Let's say that in our code, here in our code, we did this at runtime. So when we finish using this linked list, we need to delete it, right? So we will going to delete using the free command, the same command the same function you used in your assignment. So here the reset, and we call ll reset here, and also we pass the head to it. Now we will use recursive. So for sure we are going to call the reset, yeah, not the next, and we stop when we reach to node.next equal to null. It's the same way of we used for print. Let's print some message, print. Oh, okay. Printf. The linked list is empty now, and make a return. Okay. Else, and by the way, here also we need to say, let's delay it. Sorry. Here we use free, and we use the address of the node. So node, we say free node, and node is a pointer, so it's an address. Okay. And before this, we should we should here use a temp value. Let's call it node temp, because if you made the free here and then you call it node and for the reset, this is already will be deleted, so no way to access it. So first of all, we need to say node temp equal to the node next. Sorry, node next, and here use temp, pass it to the reset. Okay. Any questions? Yeah. So it's the same way, and also here we need to say free node before we say it's empty now. Okay. So I will use my code I've already prepared. Here reset, the same thing. I have temporary value, and here I free the node, last node, also free whenever I have. I will show you a bug I faced today. Now let's call reset, and then print again the content of the linked list. Okay, let's see here. What we should expect, that this is correct. We have our linked list 10, 20, 30, and then we call reset. When we print the linked list again, it should be something like only X, because when he goes, or when it goes to print, it will find null. It should stop directly. It should print X and stop. But what we see here, that we have here the values. You see, and this is clearly random values. This is big numbers, so it's random values. What happened, or what I found, like, look, if I took this code, this is why it's important you have such problems in real life. When I took this code and just put it in another compiler and run it, run please. Stop. Maybe this is not correct. Okay, you see, here is correct. The same code, I just copy it. Here in this compiler or in this machine is correct, but here it's not correct. This is because the version of the compiler may change. The content after deletion may be assigned to a random value, or maybe the address after you delete something, use it very quickly, this address, and assigned a value to it. So you end up with a situation like this. You expected it's null, but something is happening. So you should also, if you want to be very precise, you should also, before you delete, assign to next null, and assign to next null here. Now, when we execute this, let's see, X, only X. So we solved this problem. So now we have our code. We can reset and print the content. So I think linked list is now clear for you. I mean, we built the code by our hand. from 0. Let me check if we missed any concept. Empty, okay. Okay, so if you notice that the way in C, like you have too much details to do by hand. I mean, here in this code, you need for each node to create it and then get access to data and then make sure that you assign the next to the address of the next node. Yeah, so maybe you forget to, let's say for the head, let's see here, for example, you forgot to do this. So all your code will stop working. You need to look, oh, what I forget, and then you find that you forget this important line. That's why I prefer to use C++, because all of these details can be handled in one place. So instead of repeating for each node the next and the data, you simply, when you create the node, let's say here, if you have the class node, or not a class, if you have the linked list, it's, let's say, list. If it's already created, list dot add, you simply say 10 or 20 or 30. Inside add, you do all of the stuff. You link each node with the other one inside the class. So that's why I prefer using class instead of linked list. Instead of C. There is one concept we said that we are going to talk about it, but let me check how much time we left. Okay, let's take a break, 2 minutes, and continue. Okay, so let's continue. Now we are going to talk about the deconstructor, and again, deconstructor is the opposite term of constructor. So what we call at the beginning of the creating an object, we call the destructor at the end of lifetime of the object. We call the period of using the object is the lifetime. So when you finish using the object, this means you reach to the end of lifetime. Like you see here that the term when object reaches end of lifetime. We can call delete, and this, when we say delete, again, when we see like any place we see delete, here an object name, we know that there is a deconstructor is going to be called. The deconstructor has a very similar way of, or very similar style of constructor. So let's say here class linked list, and we have here the constructor. And again, you remember the constructor, how we define it? Yeah, but I mean the name. How can we pick any name we want? Can we name it, for example, only linked? It should be. It should be the same name of the class. Yeah, so it should be linked list, the same name of the class. And then we put here, let's say, integer data. And inside it, let's say here we have data. We say data, or this dot data, this dot data equal to data. Okay? The deconstructor is the same way, but just we add the approximation sign, this sign, and also we use the same name of the class, linked list. Okay, and here you do whatever you want to do. For example, you want to say to the user that you are deleting this object, cout delete the object, and then end L. So this is the deconstructor. The deconstructor. And actually what usually done in the deconstructor is whatever resources you allocate, you just release. So you use free, for instance, like this example, or delete. Because in C++ we use, instead of free, delete. So here, for example, we are allocating here a buffer. You know the term buffer? Yeah, it's a size of memory. We use it temporarily, and then we may stop using it. So here we create a buffer, just a random example, using new char, and the size of the buffer size could be 50 bytes or 12 bytes, whatever. When we reach to the end of our object, we call delete the object name of widget. Inside it, we just free the pointer, buffer pointer here, just like this, simply. Thus, this way you make sure that what you allocated in runtime, when you reach to the end of lifetime, you just free the resources. And this is the most important part of deconstructor. Any question? So, let us do this as a code. Let me allow for the sun to enter. Can you access to the GitHub repository and take the code from there? Let me show you how to. You go to the link. You have the link. You should, when you enter to GitHub, you should see it, or see it from the history of your browser. Yeah, so it's in slides lab 3, linkedlist.cbb. Now, if you want to copy the content, you either do this or simply click to row. This will gives you the file in CBB. So just copy paste the content. Sorry? Yeah. Copy all of it. So let's make a quick revision of our code. We have, again, the class, which is simply a struct. I mean, you just imagine like we removed struct and say class, and we have data and next. And simply when we create node, we make sure that our initial value is correct, 0 and null. When we assign, when we create node, we just assign the data to the data field or data. This we call it attribute in the terms of class. The linked list contains of head, and the head while constructing is null. When we insert a node, first of all we check if the head is null. That means we are creating our first node. So we assign the head to our created new node. And here now you should be, the code should be more clear to you. New is the function to create a allocation in the memory for us with a type node. So here we assign the head with the value of new node. In this case, if our linked list is empty, if it's not, we update the next of the last node we already have with the new created new node, and that's it. That's how we insert a new node. Delete node is simply deleting the node. First of all, we update the next value of the last or the previous node of our node we want to delete, and then we delete the node we have. It's not important to see all the details. This class does not have a deconstructor. So let's see how we define a deconstructor. We have now a constructor, right? So we simply say, again, the deconstructor is the same way of constructor, but we put the approximation sign. So linked list, and let us be very simple. We will say cout this node is deleted. Oh no, not this. This linked list is deleted. And then, and here I'm using, yeah, here is using the one you asked me. So using namespace, you don't need to add std each time. So add it please in your code. First of all, make sure it's executing without this addition. Yeah, create another project, just copy paste your code and run it and make sure there is no syntax error. Yeah, and there is nothing will be printed. So just add inside the class, just add the deconstructor, something like this. Linked list, let's say L, okay. Let's run the code, make sure you don't have any problems. Is the linked list is deleted? Now I will tell why. When you created the linked list, int main is just a function. I mean, you will execute and then you will have return 0. So in the compiler, anything you create, you should deconstruct before you finish executing. So here, something is in the background is going on, but you don't know if you don't have this statement is deleted. I mean, before we know the deconstructor, without having the deconstructor here, let's comment it out. Let's execute again. You would not see anything, right? That's why deconstructor is important, because something may goes in background and you may not notice it, like this case. So so this is how you define your explicitly your deconstructor. So for example, if you have here now I returned the deconstructor, the linked list is deleted to prove that this is just called when the void main, the int main stop execution or return 0. I will just put while 1 here. This make it iterate all the time. So here you will not have the deletion. Yeah, it will not stop. Now let's see the the node here. Here, the node. Let's define a deconstructor for the node here, and also see out delete the node and L. And now let's see it in a different way. Here, let's define a node. Let's call it N1, and let's use a new node, a value, and another node into another value, and so on. Now let's call delete N1, and let's see what is going to happen. I hope there is no error. Yeah, delete the node. Okay. If we want to be more sure what is deleted, we can go to, for example, to the deconstructor, where here, and say delete the node with value, and just print data, like this, with the value 10. Okay, so you are deleting N1. What if you deleted N2? It's 10. But what I want to explain that it's not magic. I mean, the deconstructor itself does what you tell him to do. So if you just want to print something to the user, it will only print the message and stop. It will not do anything. I mean, you expect when you call delete, you expect that something is going, for example, the resource is going to be cleared. But let's do this experiment. Let's just do here N1. Just like, let's see what is going to happen. See out N1 dot data. What do you think this execution output will be?
We deleted N1, so
Mm-hmm.
no value.
There is no value. Okay, let's see here. Let's see here. Put value of N1 for the node. It's called node, right? Ah, okay. It should be not like this. It's on pointer. Yeah. So the value of node is now 0. Yeah. Example of the deconstructor. Here I am trying to, first of all, I created a list using linked list. Then I printed the list. The list is empty. And inside the print, I print also the address. You are going to see something like this. This is in hexa. Hexa, if you remember, I told you there is a representation another than decimal and binary called hexa. We usually use this representation for memory, but it's not important to see the details of hexa. But this is, when you see 0x, this means that this is hexa. So I print the address of the memory also with the node. You can see here. I print the data and say it's at the address of this node. So I iterate for the whole linked list, and I print the data and each data where it's stored. Okay? So first of all, I created the linked list. It's empty. And then I added 10. And here, and you can see here, like this one is the head here. And check here. Here, let's say it's 10 here, the address. And then we added 20. And now 10 connected with 20. And this is the address of the head. This is the real address in the memory, in in your machine. Sorry? Yeah, this one is null because we only have one node. Now we have another node, so it's linked to it. And this is the other address. You can see there is a difference, right? So this is the size of, if we, I will not go to details, but this is, the difference is 16 byte. And this is the size of, if you check the size of node, just let us be sure. Size out, size of node, and here just print size of node, and then let's execute. Oh, okay, here. You see here, it's 616. Actually, this in hex, look here, when you want to change the representation while printing, like here, return the hexadecimal representation of an integer. Here in C++, you just pass, this is like a syntax. Whenever cout see that you put hex, it will change for you the representation of the number. So it was 16, right? Yeah. So now let's execute. You will see 10. This is in hex. The value of 16 is 10 in hex. Okay. So that's why the difference from 10 to 20, and actually this is 16 byte. Okay. Let's remove this. Yeah, and finally we say delete list, and the deconstructor is being called. Yeah, this example I'm showing how to delete a node using the delete instruction. So I have here the method delete node. It's the same one we already explained last session. We just take the node offset with the delete node. So you just say delete node number 1 or 2 or 3, depends about your linked list. So sorry?
Like on the internet.
Yeah.
The
Yeah, you solve it? Mm-hmm. Okay. But you did not post the code Yeah, okay. So here, I'm just showing that I'm going to create a list and then try to delete one by one. Did we explain the delete code for last session? Yes, right? Yeah. Okay, so let's see this code. Yeah, we need to just, let me make it as a new list. Oh, wait. Here, dot, 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 dot. Yeah. You can see here we created here the value a because we use hex. Let me just remove it. Hexadecimal. I'm sorry. Decimal. Yeah. Here we created with 10, and this is the address of first node. Then we added 20 and then 30 as all of our examples. Now we deleted, we said delete node 3. So it goes and deleted the last node, and then we printed the list. So we have now 10 and 20, and the last one is the none. The second node is now with next equal to none. Now we deleted the next node, node 2. So again, we only have now one node and next with the null, and then we deleted the last node, and then we printed the list, and list now we said is empty because we check in print list if the head is equal to null, then the head equal to null, then the list is empty. I think now, how much time we still have? Oh, let me check if we can take something else. Here, just here in this slide, I'm just saying that when we delete a linked list, it's better to traverse or to iterate using for the whole nodes, node after node, and delete it explicitly. This while you just go through the whole linked list until you reach to the null, and each one you delete it explicitly here. This is we already described the new and delete. Call by reference and call by copy. I think this should be for next session. Actually, this will be for next session if Abdul Hafiz Hujam said we will continue with C++. If we will continue with C, then we cannot use them. This exercise you cannot solve it because we did not took the operator overloading. Yeah, I want you to solve this exercise. I need from you to think of a way to create a linked list, but each node may have different variable type. I mean, all the exercises we solved, we have single type integer or float or something like this, right? Yeah. Yeah, it could be you could start with chart like this example and then link it with a float and then integer, or something else, float and then char and then integer. So I want you to think of a way to make your linked list supporting different data type. Okay, and also it's important to use. I put it as a hint. You remember function overloading?
Yes.
Like you have the same function, but based on the argument, you'd specify which version of the constructor is going to be called. Like here in this code, node, where is it? Here, you see, node, we have two constructors. If you did not bust anything, this will be executed. If you bust data, this will be executed. So in the same way, you will say node, this is for integer. You will say float the data. Okay? And then node char data. So based on the data you pass, this constructor will be used, or this one is going to be used. Starting from this idea, you can solve this exercise. Okay? So that's all. Good luck. Thank you. Do you have any question for anything in this session? Yeah. And by the way, this can be solved in C or in C++. It's up to you. Because the concept that you should think of is the same, but if you use C, you cannot use the overloading. Because you should have different name for the functions. Yeah, so it's up to you. I prefer to use C++, but if you could not, you can use C. Okay? And by the way, I think you will not have resources on the internet how to solve this. So it should be from your ideas only. Yeah. You will find code. I already searched, but it will not be simple, and it will not be the solution I want. Okay? Yeah. Just to give you another hint, if you used overloading, you should have a way to know each node has which type. So you may, for example, introduce a new variable saying that this node has this type as a new member for the node. Like node has data and next, right? You may introduce a new thing other than data and next, and using it, you say that this node is float, this node is integer, this node is char. Okay, is it clear? Yeah, okay. Thank you.